Hello, my name is Chloe French, and in this video I'll be explaining the variation of air pressure and temperature with relation to the altitude. So at the end of this we should hope to have one equation that's related to temperature and one equation that is related to the pressure. So we're going to start by giving some equations that we're going to need throughout this process. We are going to start with this one, which is the one for statics, which is dP over dz equals negative rho, there we go, g, where rho is the density of the gas. For the second equation we're going to use, we are going to be using du equals SQ, which is the small amount of heat change, minus P dV. The third equation we're going to be needing is the ideal gas law, which, as we know, equals PV equals nRT. But for this, we're going to assume we just have 1 mole of gas, so we're going to go ahead and get rid of our n. For our next equation, we're going to be using CV equals dQ, I think that might be du over dt. Yeah, I think it's du. Where CV is the capacity of the volume, heat capacity of a specific volume. Similarly, CP equals CV plus R, where CP is the heat capacity at a specific pressure. These are equations we're going to be using to find our equations. So first, we're going to start by using our first equation, the one with statics, and the third equation, the ideal gas law. Here we go, I'm getting myself lined up. We're going to start with dP over dz equals negative rho g, so just rewriting that one. I'm going to change this to, I'm getting myself lined up, dP over dz equals negative mg over, I'm skipping something. It's negative mp over r times g. So where the m is the molar mass. We just switch some stuff in for that. So then we're going to do some rearranging, and we're going to have our temperature over our pressure, dP, equals negative mg over r delta z. So we just did a little bit of rearranging to get this easier to work with. So now what we're going to do is we're going to integrate both sides. So we're going to write it as the integral from P1 to P2 of T over P dP. And this is going to equal the integral from Z1 to Z2 of mg over r delta z. Alright, so from here we're going to leave the left side because it's a little bit much, and we're just going to integrate the right side. So we're going to have the integral from P1 to P2 of T over P dP equals negative mg over r d z. So this is an equation that we're going to need later. It's going to come super handy. So we're going to go ahead and outline this one, and then we're going to move on to our next one. There we go. That's our work for that. Our original equations and our work, and the equation that we're going to keep in mind for later. So now what we're going to do is we're going to use the equations that we have to try and just get temperature by itself. So we're going to use a different set of equations this time. We're going to use du equals SQ, which SQ minus RT over V. I already did some substitution here, but we know that for this one it's adiabatic, so the change in heat should be 0, which is why I crossed that out. So du equals 0 minus RT over V dV But these are the same steps, so I'm going to go back and erase on the left to show you where what you need to substitute. So that was not the original equation. I skipped a little step. So that is P, and then we changed the P to the RT over V because we're working in dVs. So now we're good to move forward. So from here, what we're going to do is we're going to write that CV dt equals negative RT over V dV. So we're changing that up a little bit. So CV, we're going to take the integral. So CV from T1 to T2 of dt over T equals negative R, and the integral from V1 to V2 of dV over V. So from here, we're just going to do some easy algebra and integrate it. So CV, the natural log from T2 over T1 equals negative R, the natural log from V2 over V1. We're going to continue to do some algebra right here. Get all my work together. So we're going to write it as the natural log of T2 over T1 equals the natural log of V2 over V1, and this is to the power of negative R over CV. I'm going to keep going, just trying to get T by itself, so that's what we're trying to do here. So we're getting a little closer, so T over T1 equals V over V1 to the negative R over CV, so we got rid of the natural logs. T over T1 equals, so now what we're going to do is going to sub in the ideal gas law. So we have RT over P equals RT1 over P1 to get rid of the volume. So we're going to cancel out our R's because those are, they cross each other out. And then we're not going to cancel the T's or the P's because we have regular T's, and then we also have T1s and P1s and those things. So we have T1 over T2, but that's not quite right. It should be T over T1. Yeah, let me fix that. So T over T1 equals T over T1 times P1 over P, so we just did a little rearranging, and it's still to the power of the negative R over CV. So we have T over T1 on both sides, so we're going to get that together. So we're going to do T over T1, and then we're going to make sure the exponents are the same. So we have R over CV, but now we're adding 1 to it, because we had 2 of them. So same thing, we have P1 over P, and that is to the power of R over CV. And just change the powers to get our T and our T1s together. And so one on the left and one on the right, we want to keep them together. So we're going to go ahead and write another equation now to make this a little bit easier for us. So it's R over CV plus 1 equals CP over CV. And we're going to call this gamma. So from now on, when we're talking about this, which will mostly be in the exponents, we're going to call it gamma, so we don't have to, it's a lot to write, we could get lost. Gamma will keep us a little bit more organized. So we're going to use that from here on out, so I'm going to sub that in here. So we're going to write it as T over T1 to the gamma equals P over P1 to the gamma, gamma minus 1 and here we go, we're just going to keep going, T over T1, P over P1, gamma minus 1 over gamma. So we're almost done. This is our last step. We're going to divide the T1s over, so T equals T1, P over P1 to the gamma minus 1 over gamma. So this is what you're trying to find. We have an equation for temperature now. So now that this equation is finished, what we're going to do is we're going to go back and plug in that equation we just got into the original equation we got, and we're going to put the t's into the integral to make it a little bit easier for us to integrate. So that is what we are going to do now. Let me get all organized. Alright, so I'm just going to go ahead and start plugging that in directly because we already have our equations out. So we're going to do integral from P1 to P2. And we're just going to go ahead and plug in our stuff. So instead of having just t on the top, we're going to have t1 and then p over p1 to the gamma minus 1 over gamma. And we're just going to have our p on the bottom again, dp. So we're just plugging that right in. And then we're going to leave the stuff on the right the same as we had up above. So it's going to be negative mg dz over r. Same thing, m equals molar mass, g equals gravity, r is the gas constant. So working with the same stuff. So now we're going to go through and we're going to take out all of our constants. So t1 will be constant, p1 to the 1 minus gamma over gamma would be constant, and then we're going to keep our integral the same. So integral from p1 to p2 of p to the gamma minus 1 over gamma minus 1, because we got rid of some of the stuff in there, and that's still to the dp. So that's what we got. We're keeping the stuff on the right the same again, not too much change over here, so the negative mg delta z over r. So now what we're going to do is we are going to get all the constants and stuff on the same side and just the integral on the left. So that is what we're going to do here. Negative mg delta z over r t1, because we divided that over times, p1 to the gamma minus 1 over gamma equals the integral from p1 to p2 of p to the gamma minus 1 over gamma minus 1 dp. So now we're actually going to take the integral finally. So we've had this integral since the beginning and now we're actually doing it. So we have p to the gamma minus 1 over gamma and then gamma minus 1 over gamma. And this is going to be integrated from p1 to p2. I'm going to plug all the stuff in, so p2 from the gamma minus 1 over gamma minus p1 to the gamma minus 1 over gamma all over gamma minus 1 over gamma. And then once again the stuff on the right side stays exactly the same. So go ahead and put, I will get my screen together so you can put all the stuff together. So p2 to the gamma minus 1 over gamma minus p1 to the gamma minus 1 over gamma. And this is going to equal the same stuff as before. The negative m g delta z over r t1 p1 to the gamma minus 1 over gamma, and then now we're multiplying the gamma minus 1 over gamma that was over to the left before over to the right. So that's what we did in that step. Because what we're trying to solve for here is for the pressure. So at this point, we're getting close. We're trying to solve for the pressure. So now we just gotta, simplify, get P2 by itself. We're getting there. I'm gonna get all my stuff organized so that we can keep going. So we're going to do P2 to the gamma minus 1 over gamma, and that's going to equal P1 to the gamma minus 1 over gamma. So we pulled this out because it was on the left and on the right, so we're going to pull that out, and we're going to do 1 minus the stuff that we had before. So this is helping us get the stuff on the left a little bit more simplified because we're just trying to solve for P2. So here we go, we're multiplying it by gamma minus 1 over gamma again. Alright, we're getting closer because right now we just have P2 to the gamma minus 1 over gamma. So now what we're going to do, let me get rid of this, don't want it to get in the way. Let's keep going because we're almost done. So this is our final step for our pressure. So the pressure equals P1, fix this, P1, same kind of stuff as before, gamma minus 1 over gamma. Oh wait, no, because we're taking it to the power, so let me fix this. Same thing, 1 minus mg delta z over RT1, the gamma minus 1 over gamma. And here's where we're putting that power, because we're multiplying it, like kind of putting it over to the other side. So this would be to the power of gamma minus 1 over gamma, the whole thing, including the P1, so not just P1 gets it. So this is the final equation for how the pressure is related. So we're almost done. We have the equation for the pressure. Now we just need the equation for the temperature. So we're just going to plug this in really quick with one of the equations we found before, where T equals T1, P over P1 to the gamma minus 1 over gamma. So same thing we've got going on, and we're just going to plug it in. So our T is going to equal T1, 1 minus mg delta z over RT1, and then gamma minus 1 over gamma. So this is going to be our final equation for the temperature. So these are the two things we wanted to find, and this is what we have found. Here's all the work showing us how we got there, our two equations that we hoped to find in the beginning, and we actually did find in the end, one for the pressure and one for the temperature. All right, thank you.